NASA never expected that a routine sample return mission would rewrite our understanding of how life began. When OSIRIS-REx touched the surface of Asteroid Bennu, the team anticipated dust, rock, and little else. But what returned to Earth stunned every scientist involved. A mysterious substance, completely unfamiliar, hidden within a fragment of the solar system's earliest history. What exactly did NASA find, and what does it mean for us? When NASA approved the OSIRIS-REx mission, the goal seemed simple enough. Travel to a near-Earth asteroid, collect a small sample, and bring it home. But Bennu was no ordinary asteroid. Scientists believed it was a pristine relic from the earliest days of the solar system, a time capsule frozen for more than 4.5 billion years. If anything in space could answer the question of where our water, our organic compounds, or even the ingredients of life came from, it was Bennu. OSIRIS-REx was part of NASA's prestigious New Frontiers program, joining missions like Juno and New Horizons. Launched in 2016, it spent 2 years cruising through deep space before finally arriving at Bennu on December 3, 2018. From the moment the first images came in, one thing was clear: Bennu was unlike anything scientists had fully anticipated. Early radar models had predicted a relatively smooth world, perhaps coated in fine dust, ideal for sampling. Instead, Bennu resembled a cosmic rubble pile, jagged, chaotic, and covered with boulders the size of cars, houses, and even football fields. This complicated the mission immediately. The sampling mechanism, known as TAGSOM, required a safe, relatively flat surface to perform its delicate touch-and-go maneuver. But on Bennu, flat surfaces were almost non-existent. The asteroid's low gravity and rapid rotation had sculpted it into a spinning top shape, with loose rocks migrating toward the equator and piling up there over millions of years. Still, scientists pressed on. OSIRIS-REx's instruments began mapping Bennu in unprecedented detail. As the spacecraft orbited at an astonishingly close altitude, barely 1.75 kilometers above the surface, it created the highest resolution global map ever made of a celestial body. Spectrometers scanned Bennu's mineralogy, chemistry, reflectivity, and thermal properties. What they found shocked researchers: hydrated minerals, clay particles, evidence of water. Bennu, a half-kilometer-wide chunk of rock floating in the void, contained materials that could only have formed in the presence of liquid water. That meant Bennu must have broken off from a much larger parent body, one with liquid water flowing through it billions of years ago. This parent body might have been an early protoplanet, a water-rich object that no longer exists. The minerals preserved on Bennu were like a chemical fingerprint of ancient oceans long vanished. But Bennu wasn't just preserving the past. It was active. OSIRIS-REx detected small particle ejections, tiny explosions flinging pebbles into space before they drifted back down to the surface. Scientists believe this activity may be caused by Bennu's rotation gradually speeding up due to the Yorp effect, a subtle force created by sunlight. Over millennia, this invisible push can spin an asteroid faster and faster, slowly reshaping or even destabilizing it. Every discovery reinforced NASA's belief that Bennu was one of the most valuable scientific targets in the solar system. But all of this mapping, scanning, and analyzing ultimately served one purpose: choosing the perfect site for sample collection. And with Bennu's unexpectedly dangerous terrain, that decision would become one of the most challenging parts of the mission. Selecting a landing site on Bennu proved far more complicated than NASA had ever anticipated. Before OSIRIS-REx arrived, scientists expected a relatively smooth asteroid, something with gentle slopes and areas of fine-grained regolith, where the spacecraft's sampling arm could safely collect material. But Bennu shattered those expectations. Instead of soft terrain, OSIRIS-REx found a world covered in jagged boulders, steep cliffs, and treacherous fields of rubble. The asteroid was more hazardous than any small body NASA had attempted to study up close. The sampling mechanism TAGSUM needed a clear patch of ground, roughly 25 meters in diameter, to safely perform its touch-and-go maneuver. Bennu offered no such place. The mapping team had to reconsider their entire strategy. Over the course of a year, OSIRIS-REx conducted an incredibly detailed survey, gathering images, spectroscopic data, and topographic maps to help scientists understand the true nature of the asteroid's surface. Gradually, 4 candidate sites emerged: Osprey, Kingfisher, Sandpiper, and Nightingale. Each was smaller than NASA had hoped for, but each was relatively free of large boulders, an absolute necessity for the success of the mission. Interestingly, all the chosen sites followed a bird theme, continuing the tradition begun when Bennu was named. The asteroid received its name from a third-grade student who believed the spacecraft's sampling arm resembled the elegant neck of the mythological Egyptian heron Bennu. NASA embraced the symbolism, and the landing sites inherited avian names as well, marking each location as a potential birthplace of scientific discovery. Among the 4 finalists, Nightingale quickly rose to the top. The site lay inside a small young crater, where freshly exposed material offered a pristine window into Bennu's interior. Younger surfaces on asteroids are especially valuable because they preserve chemical clues that haven't yet been degraded by sunlight or micrometeorite impacts. Nightingale also appeared relatively smooth compared to its surroundings. It was small, far smaller than NASA had originally planned for, but it met the minimum requirements for TAGSUM to operate. As OSIRIS-REx orbited Bennu, the team's anticipation grew. The spacecraft had already provided unprecedented insights into the asteroid's structure and history, but the sample collection would be the moment that defined the mission. For months, scientists tested OSIRIS-REx's navigation systems, its thrusters, and its sampling arm. They needed total confidence before attempting a maneuver that would bring the spacecraft within centimeters of Bennu's unpredictable surface. The first rehearsal, conducted in April 2020, brought OSIRIS-REx within 65 meters of the asteroid. Everything worked perfectly. The spacecraft approached smoothly, performed its burn, and returned to a safe position. A few months later, in August, OSIRIS-REx conducted a second rehearsal, descending to just 40 meters above the surface. Once again, the test was a success. Every movement, every thruster burst, every sensor reading indicated that the spacecraft was ready. But rehearsals could only prepare the team so much. The real challenge lay in the unpredictable physics of Bennu itself. With such weak gravity, the asteroid's surface behaved more like a loosely held collection of gravel than a solid rock. Any miscalculation could cause the spacecraft to collide with a boulder, sink unexpectedly into the surface, or fail to collect a meaningful sample. Nightingale offered promise, but not certainty. As OSIRIS-REx prepared for its historic descent, the mission team understood the stakes. This would be NASA's first attempt to retrieve a physical sample from an asteroid, an opportunity to bring untouched material from the dawn of the solar system back to Earth. Every detail mattered, every calculation had to be perfect, and every moment of the mission had led to this: a daring, delicate attempt to reach out, touch an ancient world, and carry its secrets home. On October 20th, 2020, after years of planning, rehearsals, and orbital surveys, OSIRIS-REx began its final descent toward the Nightingale site. Unlike most spacecraft operations, this maneuver could not be controlled in real time. Signals from Earth took too long to reach Bennu, so OSIRIS-REx had to perform every step autonomously, relying on onboard navigation, imaging, and hazard detection algorithms. It was a moment where preparation met uncertainty. As the spacecraft approached, it raised its solar panels into a protective Y-shaped position to shield them from the debris cloud that would soon erupt. The tagsome arm extended downward, ready to make contact with Bennu's unpredictable surface. Each meter of descent carried risk. Bennu's gravity was so weak that even a slight push or miscalculation could send the spacecraft drifting off course or colliding with hazardous terrain. At last, tagsome touched the surface, and something completely unexpected happened. Instead of meeting resistance, the arm sank deep into Bennu, plunging nearly half a meter into what behaved more like loose foam than solid rock. Bennu's exterior, once thought to be firm, was revealed to be a fragile mix of loosely bound rubble with hidden voids between the particles. OSIRIS-REx wasn't landing on a surface, it was falling into it. In that instant, tagsome released a burst of nitrogen gas. The explosion of pressure blew apart the surrounding material, lifting rocks and dust into a frantic cloud. Instead of a gentle splash of regolith, more than 6 tons of debris were ejected into space, scattering in all directions. OSIRIS-REx's thrusters fired in a dramatic escape burn, pushing the spacecraft away from the destabilized surface as the debris expanded behind it. When the dust settled and engineers examined the data, they realized tagsome had collected far more material than anticipated. The mission required just 60 grams. OSIRIS-REx had gathered over 400 grams, possibly more than a kilogram. In fact, it collected so much that a rock jammed the sampler head's closure flap, causing some material to leak into space. The priority immediately shifted from maximizing collection to securing the precious sample for return. Despite the challenges, the touch-and-go maneuver was a complete success. OSIRIS-REx had accomplished one of the most delicate operations in the history of planetary exploration. It had reached out to an ancient world, touched it, and captured a piece of the solar system's earliest history, an achievement that would open the door to discoveries no one had imagined. With the sample securely stored inside the return capsule, OSIRIS-REx began the long journey home. After spending more than 2 years orbiting and studying Bennu, the spacecraft performed its final flyby on April 7, 2021, capturing images of the dramatic crater it had created during touchdown. Bennu's surface was visibly altered, large rocks had been displaced, and the sampling site was transformed. But there was no time to linger. 7 years of interplanetary travel had led to this moment, and now the spacecraft carried one of the most scientifically valuable treasures ever collected: pristine material from the dawn of the solar system. After traveling 1.9 billion kilometers on its return trajectory, OSIRIS-REx approached Earth in September 2023. The sample capsule separated from the spacecraft at a distance of about 100,000 kilometers above Earth. Its descent through the atmosphere would be violent, fast, and precise. Entering at nearly 43,000 kilometers per hour, the capsule became the second fastest human-made object to plunge through Earth's atmosphere. Temperatures soared to around 2,700 degrees Celsius, half the temperature of the sun's surface. But the capsule was protected by an advanced heat shield made of pica, a special ablative material that vaporized layer by layer, carrying away heat and keeping the precious sample below 75 degrees Celsius. After decelerating, the capsule deployed its parachutes and drifted toward its landing zone, a rugged section of the Utah Test and Training Range. From entry to touchdown, the entire descent lasted approximately 10 minutes. Recovery teams, previously trained and rehearsed for months, quickly secured the capsule, placing it in a clean environment to avoid contamination. Soon after, it was transported to NASA's Johnson Space Center, where scientists eagerly prepared to open it. But even this step came with unexpected challenges. The capsule contained a surprise. Before the inner canister was even opened, 70 grams of loose rocks and dust were found scattered throughout the outer compartment. This bonus material had managed to escape during transit due to the jammed flap caused by a lodged rock. While this material was scientifically useful, it wasn't as pristine as the sample sealed inside. Accessing the inner canister proved difficult. 2 of the 35 fasteners holding it shut were stripped by Bennu's dust, making them impossible to remove with existing tools. NASA engineers designed a new custom screwdriver-like tool made of a special non-magnetic stainless steel that met the strict clean room standards. After months of delicate work inside a nitrogen-purged glove box, the curation team finally succeeded. The inner sample was revealed. Another 51 grams of pristine Bennu material lay inside, bringing the total to more than twice the mission's target amount. Once cataloged, the sample was divided for study. At least 70% will be preserved for future generations, much like the Apollo lunar samples. But the initial analysis already revealed extraordinary findings. Inside the dust were presolar grains, microscopic crystals that formed before the sun itself existed. These grains preserved chemical signatures from ancient stars, including supernovae. Bennu's sample contained 6 times more supernova dust than any previously studied astromaterial. Scientists also identified a wealth of carbon and nitrogen-rich compounds, including 15 of the 20 amino acids essential to life on Earth. Even more astonishing, researchers detected all 5 biological nucleobases: adenine, guanine, cytosine, thymine, and uracil, the molecular foundations of DNA and RNA. These were not traces, they were abundant. But the breakthroughs continued. A Japanese research team discovered sugars essential to life, including ribose, and, for the first time ever in an extraterrestrial sample, glucose. Ribose is central to RNA, supporting the hypothesis that early life may have relied on RNA-based chemistry before DNA evolved. NASA researchers also identified a strange new substance, nicknamed space gum, composed of nitrogen and oxygen-rich polymeric materials. This mysterious compound, layered on mineral grains, resembled an extraterrestrial cousin of polyurethane. Such complex molecules may have served as chemical precursors for life in the early solar system. Even more compelling, scientists found clear evidence of Bennu's watery past. Hydrated minerals, clay particles, serpentine rock, pyrrhotite, and even phosphate, all indicators of long-standing interactions with liquid water. These discoveries suggest Bennu once belonged to a much larger parent body, potentially a water-rich world with active chemistry. The Bennu sample is already rewriting our understanding of how planets, and possibly life, form. And the work has only just begun. The OSIRIS-REx mission did far more than collect a sample. It opened a doorway to understanding the origins of our solar system, the chemistry that shaped early Earth, and the ingredients that may spark life throughout the universe. With the Bennu material now secured on Earth and distributed among laboratories worldwide, researchers are only beginning to uncover its secrets. The discoveries so far have already exceeded every expectation, but what comes next may be even more profound. For decades, scientists have relied on meteorites to study ancient cosmic material, but those samples were altered by fiery atmospheric entry and Earth's environment. Bennu's sample is different. It is untouched, pristine, and perfectly preserved, frozen in time since the earliest days of the solar system. Every grain carries clues about the stars that existed before our sun, the chemical reactions that occurred on long-lost parent bodies, and the distribution of life's building blocks across space. With these clues, scientists can refine their models of how Earth formed, how water arrived, and how organic chemistry took root on our planet. The presence of amino acids, nucleobases, sugars, hydrated minerals, and even the mysterious space gum suggests that complex molecules were abundant long before Earth existed. This supports the theory that the ingredients for life were widespread, drifting between worlds and delivered by asteroids much like Bennu. And the discovery of materials shaped by water indicates that Bennu's parent body may once have been geologically active, perhaps a mud-rich world with warm interiors and chemical reactions resembling those on early Earth. Yet Bennu's scientific importance goes even further. It is also classified as a potentially hazardous asteroid with a small but notable chance of impacting Earth in the late 2010s or early 2020s. Understanding its composition, structure, and behavior is essential for future planetary defense strategies. The insights gained from OSIRIS-REx will help scientists refine models of asteroid dynamics, fragmentation, and response to gravitational or thermal forces. In many ways, Bennu is both a messenger from the past and a warning for the future. But the mission's story doesn't end with the sample return. Shortly after releasing the capsule, the spacecraft fired its thrusters and embarked on a new journey, this time toward asteroid Apophis. In 2029, Apophis will pass closer to Earth than many satellites, offering a rare opportunity to observe how such a close encounter affects an asteroid's structure and rotation. Now renamed OSIRIS-Apex, Apophis Explorer, the spacecraft will map, analyze, and even stir up the surface of Apophis, just as it did on Bennu. The mission promises to reveal even more about how asteroids evolve, break apart, and respond to gravitational forces. OSIRIS-REx was designed to answer questions about our past. OSIRIS-Apex will help us prepare for our future. Together, these missions represent a monumental leap in our understanding of the small bodies that orbit alongside us, remnants of the solar system's formation, and potential carriers of life's essential ingredients. The story of Bennu is far from over. The sample will be studied for decades, perhaps yielding discoveries we cannot yet imagine. Every new insight brings us closer to answering humanity's oldest questions. Where did we come from? How did life begin? And are we alone in the universe? If the Bennu sample is any indication, the universe has far more to say, and we're only beginning to listen. If you want to explore more discoveries like this one, make sure to subscribe so you don't miss what NASA, OSIRIS-Apex, and the next generation of missions uncover next.